with these reports. So, first of all, this is from the IPCC website describing what the IPCC is and kind of the history of it. It is a UN program and a World Meteorological Organization program that was started in 1988 to provide the world with a scientific view of what our best understanding of climate change is at the time that the report is made. Okay? And of course, a year after the report is made, more studies come out that are usually highly critical of some of the things that went into the report because new evidence has come up. Okay? That's science. Okay? The report is as it stands at the time. And another caveat is that we have to have a cutoff on papers that we can review. It's an assessment. We do not conduct research in the IPCC. We only assess the studies that have been made, sometimes by scientists, by ourselves, but mainly by other scientists, and say, what is the consensus of what we understand about climate change? Observations, attribution, and projections. Okay? And so because of that, we have to have a cutoff on papers, or else we'll have to be reading papers and changing the document until the last minute. So for the last assessment, the one that I was on, we stopped papers. They had to be submitted by July of last year, and they had to be published by March of this year. So that led to some problems in the final meeting because many papers had been submitted that had not finished the review process and were not accepted and were actually not in print and were not going to be in print by March. And so we had to pull all of those papers from the study and not comment on them. There was only a few, mainly in the cryosphere section, but it was something that we had to deal with. Okay? The other thing is it's not just a small group of scientists, like 5 or 10 or so. It's a fairly large number of scientists from all over the world, and it's completely voluntary. None of us got paid to do any of this. Yes, we got to travel, but then they made us work, okay? Sometimes from 8 to 7 o'clock at night. I mean, and we really worked. So there are 3 working groups. I was part of Working Group 1, which is the physical scientific aspects of the climate system and climate change. So basically the physics and chemistry of climate change. And this report has already been published. It was published officially in September 2013. There may be some final copy edits after that. I think the hardbound book will be published sometime in March of next year. There's 2 other working groups. I'm not really going to address what they did because they're still working to be published. This one will be published in April, this one in July. But Working Group 2 assesses the vulnerability of the socioeconomic impacts of climate change. And Working Group 3 assesses the options for mitigating climate change. Dumping lots of sulfates into the atmosphere. Bad idea, but it's something they have to talk about. So the history of the IPCC is the first report was published in 1990. It was a fairly small report. And subsequently, every 5 years or so, another report has gone out. Of course, you can't just wait 4 years and then spend a few months writing one of these reports. It actually is a 4-year process. Okay? And so I was involved in the 4th assessment report marginally as what's called a contributing author, which basically I supplied a sentence or 2 to the main authors, and then they ignored it. That's typically what happens. And then in the 5th assessment report, the one that's just been published, I was nominated by one of my good friends, Josh Willis, who was nominated for the next round by about 4 of us from the chapter, so that he can actually see what it feels like to do this. And I was accepted and selected from a group of about 200 to 300 scientists to spend about 4 years of my life working on this. And it was fun. but it was very, very hard. So there are groups of authors. So we have the lead authors. There's typically 10 or 12 for every chapter. Okay? And I was selected for the Ocean Observations chapter to be the sea level guy in the Ocean Obs chapter so that I could talk to all the other people. There was a separate sea level chapter, and I knew all of them, so I was selected as the go-between to make sure that our chapters were consistent. And that was a tough job because they didn't necessarily want to do what we wanted them to do. And then we had the coordinating lead authors, which were 2 authors that were selected, not by our group, but by the chairs of the working group 1 to kind of oversee the whole chapter and make sure it was all internally consistent. And it was ironic is that several of the lead authors have been part of the IPCC process for many, many of these iterations, but the coordinating lead authors were like me. They had never been in the IPCC process before themselves either, and so they were as neophyte as I were, but they did a great job. And we had a really good team for my chapter. And then, of course, we had these contributing authors, which, like I said, was what I'd done before, and I thought, oh, this will be easy. You know, I was a contributing author. I'll just do a little bit of writing. It won't be that tough. So yeah, I'll be a lead author. And I learned pretty quickly that it was a lot more work than I thought it was going to be. So here's the process. And so the whole report evolved out of 4 meetings. And then we had a 5th meeting, which was the acceptance meeting here in Stockholm, which just ended in September. And I was at every one of these meetings. And you go to these foreign places, you think you'll have lots of time to sightsee and everything like that, but no. You know, we go to work at 8 o'clock, sometimes to 7 o'clock at night. During these meetings, we're drafting the report. We have internal meetings to discuss issues between various chapters, hash out some of the problems that have arisen from one meeting to the next. In the second meeting and third meeting, we wrote drafts that were sent out for reviews, and I'll talk about that in a minute. And so at the subsequent meetings, we actually had to look at those reviews, discuss how we would reply to those reviews. And this was a very involved process. And of course, every single one of these drafts was leaked. And I'll talk about what happened. And the process should probably be changed to avoid that. But one of the things about the IPCC is they want to be completely open and transparent. And that's one of the things that a lot of the deniers and skeptics criticize us, is that we're not open enough. I don't know how you could be much more open than what the IPCC is and get things done. So let's talk about these reviews. So most of you have written papers. You've sent it out for review. And either the editor picks the reviewers, or you say, here's like 4 experts that I think could do a good job of reviewing this paper. Well, the IPCC has these expert reviewers as well, and some of them are people that we select, but then we say people can self-nominate themselves to be an expert reviewer. And that could be any Tom, Dick, and Harry who signs up and says, I am an expert in sea level change. And we had plenty of people who reviewed the chapters who were proclaimed experts in the field, and they wrote comments, and we had to reply to every single comment that came for the review. So for a typical review of a paper, you might get, you know, a couple of pages of reviews, mostly well thought out. Here we've got about 50 pages of reviews for every single draft that we put out. And that was just for my chapter, and every single chapter got ones like that. So it was a very tedious process to go through those reviews. And then we had the acceptance meeting. Well, right before I went to the meeting, there was a lot of press about it, about the IPCC was convening a last-minute emergency meeting to change the report because skeptics and deniers had shown a problem with it. Well, that was bullshit. Okay, sorry. The meeting had been planned 4 years earlier, right? So we knew this meeting was happening, and it was part of the process. And part of the process is the scientists write the main report. Then it is distilled into what's called a technical summary. And then that technical summary is distilled into what's called a policy summary for policymakers. Okay? And in each level, the language is changed subtly so it's more applicable to the intended audience. And so at this meeting in Stockholm, the whole goal of that was that we responded to the governments had questions and to try to negotiate the language of how we describe some of these things, right? So scientists write in a very particular way that is not necessarily conducive to a politician to understand what we mean. And so part of this was to negotiate the language so that the science was not lost, but that it could be written in a way that a policymaker could pick this up and says, oh, you mean that sea level has risen by 20 centimeters instead of at 1.7 millimeters per year. They don't understand rates, but they can understand extreme numbers. And so that's just something that we had to negotiate and talk about, right? And so it wasn't a crisis meeting. This was a planned meeting. And just to prove that I was there, that's a picture of the lead authors, and trust me, that is the back of my head. But really, for this whole meeting, the lead authors were there, not the whole writing team of the report were not there. It was like about 2 or 3 for each chapter. And we were just there to answer questions that the policymakers had. If there was some particular aspect that they had a question about that they didn't understand, we were there to supply them with an answer based on the science of the main report, and to work on maybe changing the language slightly so that the meaning was still the same, the science was still the same, but it could be understood by a policymaker. And the one thing I want to point out is that the delegates that were representing the various countries, almost every single one of them was a scientist from their country. They were not politicians, right? So they understood the specifics of the report, and they had read the report probably more than I had, because I hadn't read every chapter, but they probably had. All right, so that's a little bit of the overview of the process and the meeting. So let's get into some of the details of the report. So this is the fundamental statement from the Summary for Policymakers, is that warming of the climate system is unequivocal. And since the 1950s, many of the observed changes are unprecedented over decades to millennia. Now, this is a very strong statement, and we had a lot of debate over whether we were using unequivocal, obvious, just small changes in words. But this is what we finally came up with, and there was a strong consensus to state this, right? And all the various things listed that have warmed, things that have diminished, sea level has risen, concentration of greenhouse gases have increased, okay? So this is the broad statement that we wanted to give to the policymakers. The climate is changing, and we know this because we can observe all of these changes. Okay. One thing, when we wrote the report, we had what we called confidence language. Okay. Some of these are based on statistical testing, but some of them are based on how much information we have, how much different lines of evidence we have, and whether different groups looking at this evidence reach the same conclusion. Okay? And so this is a little bit subjective, but the idea here is that if you have one set of data and you have one group looking at it, then you have limited evidence and low agreement, right? If you have one type of data and you have a lot of groups looking at it and they all see the same thing, then you have limited evidence and high agreement. And really, that gives you a little bit more confidence, probably medium confidence that what you're observing is a real climate signal. But if you have multiple lines of evidence, many data sets of different things, sea level, ocean temperature, salinity, atmospheric temperature. And lots of groups are looking at it, and they're all seeing the same thing. Then that gives you high agreement, robust evidence, and you have high confidence in the results that you're getting. Okay? And again, we also use likelihood definitions in the text. Okay? And those are defined, and we only use those statements when there is a statistical testing that could be done that could quantify the likelihood of this. Okay? So, in general scientific testing, you often say, oh, it is likely that this is true, or it's very significant. But in the IPCC report, those terms actually have a definition, right? And so the ones that you'll see most often are likely, which is a 66 or greater % probability, very likely, which is greater than 90% probability of being correct, virtually certain. There are a few things we are virtually certain of. Sea level is rising. We're virtually certain of sea level is rising. Now, the rate at which it's rising, we are probably more like very likely. Okay? There are some things that we could be about as likely as not. It's not really clear. It's closer to 50%, one way or the other. We're not really sure. Okay? And so when I am describing some of the results, these language will be in the text. All the text I have here is quoted from the report, and they're all italicized. Okay, so they actually have meaning. Okay, so let's start going through the figures. So the first one I want to talk about is surface temperature. Okay, it's a combination of sea surface temperature and a combination of air temperature at the surface. It's not exactly land temperature, it's air temperature at the surface. So on the top is 3 records. Only one of them goes back to the 1850s or so. And of course, there is some extrapolation and interpolation of the data in the past because we don't really have good global records. But you can see consistency among the data sets. And this is a very nice representation of this data up here. All it is these data that have been averaged over 10-year blocks. The grays are the uncertainty on the one that has the best considered uncertainty estimate of it. And then you have the various values in here in different colors. And the key point here is notice this range right here. Each of these decades, 80s, 90s, and 2000s, have been successively warmer than the decade before outside of the error bars. Okay? And these are the 90% confidence. So that means that there is a high statistical difference between these decades, right? And that's what it said, is that it's successfully warmer at the Earth's surface in any preceding decade since 1850. We know that from the observations. There's other evidence, not in this plot, but in the underlying document, that states that in the Northern Hemisphere, this period from 83 to 2012 was likely the warmest 30-year period of the last 1,400 years. Even warmer than during some of the medieval warm periods. Okay? There's medium confidence in that because there are only a limited amount of observations, but a lot of people have looked at it. All right, so let's start talking about ocean temperatures. So we have fairly good records of ocean temperature to depth, starting in about 1970 with the XBT program. There have been a lot of changes since the last assessment and the new assessment, mainly due to finding errors and biases in a lot of the temperature data in the 1970s and 1980s. And in fact, we have a lot more robust evidence of warming in the ocean than we did in the previous assessment in 2007. And all the plots here from 1971 to 2010, these are linear trends estimated from the temperature data. And this is averaged over 0 to 700 meters depth. That's where we have the most temperature profiles. And you can see robust warming here in the Atlantic, North Pacific, and even in the Southern Ocean. There's some areas where there's actually temperature drops, but overall temperature has been warming throughout most of the ocean.
What was the color coding?
The color coding? Oh, I thought I had that on there. I took it off. It's on the next one, actually. That's it. It's like -3 to +3 degrees C. And so here's another look at that data. This is from to depth, and these are zonally average temperature trends. And for latitudes, you can see the warming in the north. The tropics, it's warming in the surface, some slight cooling down below, indicating changes in the thermocline depth over that time period. And then in the southern hemisphere, a large, very coherent warming throughout most of the column there in the upper surface. Here we can see it as it evolves in time. Again, 700 meters depth. These are global averages. And we can see the cooling in the surface, or the lower temperatures in the surface rising to warmer temperatures, and how it's really expanded into depth over this time period. And here's kind of the evolution of it at time. And from that evidence, it is virtually certain that the upper ocean has warmed, right? So this is one we're virtually certain of, 99% confident that the ocean has warmed. It is likely that it warmed from the 1870s to 1971. That's based on more limited evidence. It's based on a few hydrographic sections that were repeated over time, and there is evidence of warming from that data. Okay? The other thing that's important is not just the temperature, but the heat that the ocean stores and how that's changing. And why that's important is because that gives us a good feel for the energy imbalance of the Earth. Because essentially the ocean can hold so much more heat than any other component of the Earth system. It gives us a good feel for what the energy imbalance of the Earth is. And here we have multiple observations based on the various different temperature data sets of the estimate of the upper ocean heat content. They differ mainly in the corrections that they apply to the temperature data for the fall rate and in their methods of mapping the data. And you can see that some of them are a little bit more change over this time period, some are a little bit less. The ones that are a little bit less generally relax to assuming a zero change if they have no data, which is probably a little bit biased than assuming some of these other ones that it is kind of a global average or a zonally averaged change in heat. The purple is probably the one that we trust the most, and its error bars are probably the ones that are the most realistic. And if you see, all these other estimates fall within the error bars of the purple one, and they all show a significant warming from about 1971 on to 2010, right? And from that, this should be italicized. It is virtually certain that the upper ocean heat content increased as well. The upper ocean temperature has increased, the upper ocean heat content has increased as well. And this is why it's important. It's 93% of the energy imbalance of the Earth. You think about the global warming being the air temperature warming, but that's a very small amount of the energy that's being stored from the energy imbalance. Almost all of it, 93% of it is going into warming the ocean. There's a smaller fraction that goes into melting ice, and that's been growing in time, and then another fraction that goes into warming the land. The deep ocean is actually warming as well. Okay, here we have observations from 700 to 2,000 meters depth from about 1957 to 2010. And we have some observations from the 90s to 2000, a very, very deep ocean of warming of the deep ocean. The error bars are 90% confidence for both of these. And we can say that there is a significant rise in the heat storage in the deeper part of the ocean as well, which is what we would expect as this water is mixed from the surface into the depth. It's smaller than in the surface, of course. Here we only have about 50 zeta joules maximum change, whereas the other one was 150. But it is a significant contribution to the total heat storage of the ocean. Here's a plot of these observations of the deep ocean temperature changes. These are based on these repeat hydrographic sections and taking the measurements at the very, very deepest levels where the temperature is basically constrained by the deep abysses of the ocean. And we actually see that the water is warming exactly where we would expect it to be based on the way that water mixes in the deep ocean. Basically, bottom water formation areas is where we start to see the largest temperature changes here in the Southern Ocean, and then it's spreading out due to the circulation, the deep circulation. And you can see in this figure here, and the temperature changes between 1992 and 2005 based on the global observations and just the ones in the Southern Ocean from these hydrographic sections. You can see really the surface intensification in the global ocean, but in the Southern Ocean, it's a very strong warming throughout the entire water column. Okay, so the warming is, although not as large at the surface in the Southern Ocean, it extends down much deeper over this time period. Yep.
So we normally think of two major deep water formation regions, the North Atlantic deep water and the Antarctic bottom water.
Yep.
And so we're seeing here a very asymmetrical distribution.
Part of that is
North Atlantic, not
the North Atlantic, unfortunately, is not really surveyed in these repeat hydrographic sections. You do see some warming here, which would be the pathway from the North Atlantic, but it's not significant enough.
Well, is that the pathway from the North Atlantic, since it's bottom water?
Yeah.
Is it the pathway from the North Atlantic, or the signature of what's happening in the South, in the Southern Ocean?
Yeah, it's a
matches pretty well with the North Atlantic deep water.
Yeah, yeah.
It's the Mid-Atlantic ridge to the boundary.
Yeah.
Which is the recirculation.
Yeah, and some of it could be
4,000 meters.
Yeah, some of it could be coming up here from the south, but it's also interacting with North Atlantic deep water formation. But part of the problem is, and it's a good point, there are not a lot of these repeat hydrographic sections up in the North Atlantic, which is a shame. There have been individual studies that have shown warming in that region, but there are not the repeat hydrographic sections that you can get statistically significant result. And these basically use 10 to 20 repeat hydrographic sections in order to get a robust measurement. Yeah.
Okay. But, yeah, the asymmetry is what's striking.
Yeah. Yeah. And it's also, if you look back at the temperature data here, you can see, well, we have, well, I think in the report there is actually a plot showing the temperature at depth as well, and it goes much deeper in the Southern Ocean than it does in the North Atlantic.
Could you go back, keep going back?
Yeah.
One more, no, next one. Yeah, from 2000, you're pretty flat to the present.
We'll talk about that in a little bit. So let's talk about sea surface salinity, because sea surface salinity is really our best indicator of changes in the water cycle. Precipitation on land, it's changing some places, it's not changing in other places. We can't really measure evaporation, but sea surface salinity really reflects changes in the precipitation, evaporation exchange in the atmosphere, the water cycle. And of course we know that the mean sea surface salinity follows the patterns of E minus P over the ocean, right? Where you have excess evaporation, you have high salinity. Where you have low evaporation, excess precipitation, you have low sea surface salinity. And so we can observe changes in sea surface salinity over time. And there is sufficient salinity measurements near the surface that we can actually resolve the long-term trends in sea surface salinity. And several studies and several groups have done that, and they see consistent results. Where there is high salinity, we have an increase in salinity, and where we have low salinity, we have decreases in salinity. So basically, where it is salty, it's getting saltier. Where it is where it's fresher, it's getting fresher, and that's consistent with changes in the evaporation and precipitation over time. And really, this is the best evidence we have in the IPCC report of changes in the water cycle. And again, it's medium confidence. It's not high confidence. We could only assign it medium confidence because all the groups that are looking at it are really using the same salinity data sets. Right? That's the only evidence we have. If we had precipitation and evaporation measurements that were of sufficient quality, then we could possibly give this high confidence, but we do not have those data sets. All right, just a map of the salinity at depth. So we can see changes not only in the surface salinity, but also the subsurface salinity. And this is reflecting not only the water cycling, but also changes in the circulation and density. All right, running a little bit slow here, so I'm going to speed up a little bit. Changes in the ocean circulation. We did address that. Most of the changes in the ocean circulation that we could observe over the past 50 years or so, a couple of decades, are really what we would consider multi-decadal fluctuations. We cannot see a sign or evidence of climate change, long-term climate change, in the changes of the circulation. This is just a map of sea surface height trends from satellite altimetry overlaid with the dynamic topography from Argo, and basically showing that sea level has risen in the western Pacific and fallen in the eastern Pacific, and a lot of this is related to the Pacific decadal oscillation. There is evidence that the subtropical gyres here and here have intensified and expanded slightly since 1993. There's multiple lines of evidence for that, both from the altimetry, but from in situ measurements as well. But again, we don't believe that that is related to ongoing long-term climate change. It probably reflects more the specific decadal oscillation and changes in the winds on multi-decadal periods. The AMOC, the Atlantic Meridional Overturning Circulation. That gets a lot of questions because climate models predict in a warming world, as we get more freshwater input into the North Atlantic, there could be a slowdown in the AMOC. We have lots of observations that have been put in over the last 10 years or so to try to measure the transport of the AMOC. We have the Florida current measurements, which go back to 1965, which is just one portion of the AMOC. And there's no evidence of a linear trend either increasing or decreasing of the AMOC over this time. There's a lot of interannual variability in the strength of the circulation. There's a lot of incoherence in the circulation. This is at a lower limb. This is the upper limb at two different latitudes. And you can see that they're not really coherent except in some times, right? And so there's a lot of interannual and higher frequency variability of the meridional returning circulation, but there's no direct observational evidence of a change associated with climate change. Ocean acidification. So as more carbon dioxide goes into the atmosphere, a large amount of it is stored in the ocean. And we can measure that. And we can measure the effect it has on the acidifying the ocean. These are just a couple of time series from the BATS station, the Aloha station, and STOC, showing the how pH has decreased in time, becoming more acidic. This is from Bob Byrne, actually, who was a contributing author on the chapter. Showing the results of his cruise, the differences between the cruise in 1991 and the cruise in 2006 in the North Pacific of the pH of the water. Okay? And so we have high confidence that the pH of ocean surface water has decreased since the beginning of the industrial era. Sea level. Let's talk a little bit about sea level. Like I said, there was sea level section in Chapter 3, Ocean Observations. There's also a separate sea level chapter which was synthesizing results from multiple chapters together and dealing with projections. So in the chapter 13, they looked at the paleo records of sea level, the observational records of sea level rise, and the projections of sea level rise based on models. And there's a clear evidence from multiple lines of evidence, both tide gauges, which is this purple line here. These other observations are salt marsh records, or reconstructions of sea level. There's clear evidence of a change in the rate of sea level rise somewhere in the 1800s. Okay? Sea level was fairly low from about 1800 for the last 3,000 years before that. We have other observations of that from the geological record. And then it's been higher since the mid-1800s. And so one of the statements that is in the report is that the rate of sea level rise since the mid-19th century has been larger than the mean rate during the previous 2 millennia, high confidence. And that's based on having multiple lines of evidence and many groups looking at it and all getting the same results. There has been question about whether the rate of sea level rise over the last 20 years is an acceleration or a further increase in sea level. At the moment, we can't say with any confidence that it is, because if we look at the reconstructions of sea level based on various groups using the tide gauge records, there is a period here in the from about 1925 to about 1945 to maybe 1950 where sea level appeared to be, from what evidence we have, was rising at a higher rate comparable to what we're seeing today. It has also been a little bit lower over periods of time as well. And this likely reflects some sort of natural climate variation as well. And so we cannot say that the sea level rise that we are seeing right now is necessarily an acceleration. So we have a nice synthesis section in Chapter 3. And I think it actually is a very nice statement of why the ocean observations are actually so important to understanding climate change. Because not only are the consistency of the patterns of change from a number of independent observations consistent with global warming and climate change, but it's also happening in areas that we would expect it to. It's following the physics as we understand it. So for example, this plot here is showing the change in the ocean storage of carbon, mean sea level, upper ocean heat content, and this high salinity versus low salinity, i.e. getting more saltier and less salty. And they're all consistent with what we would expect from a global warming, is increasing of all of them. We also see that we're getting warmer in the deep ocean in places where we have bottom water formation, and we're also getting saltier in the tropics where we have more evaporation over precipitation. So it's all consistent. We have multiple lines of evidence, and it's, let's see, there was a nice little phrase here that we did. The distributions of trends in subsurface water properties are consistent both with each other and with the well-understood dynamics of ocean circulation and water mass formation, right? So for example, if it was getting really warm in the tropics and not at the high latitudes, we would have kind of a question about that, because that's not where deep water forms. But because it is forming at the high latitudes, it makes sense with the physics of ocean circulation as we understand it. All right, so before moving on to attribution and sea level projections, and this brings up what Gene mentioned, this kind of hiatus and cooling that is apparent in some of the data sets and not all the data sets. So there's been considerable muttering in the blogosphere about hiatus and the warming. And there's going to be continued cooling, and we're entering an ice age, things like that. In fact, I found this headline, "Warming Low Haunts Authors of Key Climate Report." I can guarantee that none of us lost sleep worried about this. We did address it, though, because we knew that if we did not address this in the report, that that would be one of the things that the deniers and skeptics would latch on to. Oh, you're ignoring this information, right? So let's take a look. Oh, I got this from Gary a couple of weeks ago. Is that there's a letter that has been sent to Pam Bondi. Probably you can't read this, but I'll read this one little section from it. We, the undersigned, ask that your office immediately launch an investigation into the possibility of widespread official misconduct, potentially involving fraudulent activity and malfeasance by elected and appointed officials. And it's all because they are using the IPCC report and projections of sea level rise to plan what they're going to do in their communities over the next 50 years. And one of the statements here is that according to many prominent scientists, the latest global temperature measurements, it is possible that the Earth has entered a new and possibly dangerous cold climate. Well, that's bullshit. But this last bit here is true. Global oceanic temperatures and atmospheric temperatures have actually been declining for the past 10 and 7 years. They haven't been declining, but they've been more or less stable. Okay, and there are reasons for that. And so let's look at it from a couple of perspectives. So it's really in the sea surface temperature. It's not really in the air temperature records. The air temperature is still going up slightly, but the sea surface temperature has been relatively stable over the past 10 years or so. Okay? But that's not unique, right? It was very stable here in the 50s and 60s. It was actually going down a little bit as far as we can tell from the 1800s to the 1900s. There are natural climate variations on top of longer-term climate change. You should never look at a single 10-year, 15-year cycle and extrapolate what's going to happen in the next 10 or 15 years. You need a much longer time span to see the trend. Okay? The other key point here, this is just sea surface temperature. This is just really the skin temperature, the very top layer of the ocean surface. If we look at the integrated heat storage, what the total depth of the ocean is doing, this is really only the 700 meters depth, we don't really see that hiatus in the warming. The upper ocean is still warming. Okay? At depth, it's still warming as well. And it's quite possible that the surface is maybe staying stable and that heat is being transferred to deeper levels. Okay? That's quite possible. And in fact, when we address this in the report, the first thing we say is don't look at short records to estimate long trends. And secondly, we have quantified what's behind this. It's due roughly in equal measure to a reduced trend in radiative forcing. The solar radiation, the solar insolation has been slightly lower over the last 10 years than it was over the previous 10 years. This is less solar heating has gone into the atmosphere and the ocean. There have also been more volcanic eruptions in the past decade than in the previous decade. That could cause cooling as well. And there's also this possible redistribution of heat within the ocean. Okay? And so all of this will tend to explain this slight leveling off, but there's nothing that we understand about the physics that would suggest that it's going to dramatically start cooling and continue this. At some point, it should go up again. All right. Does that answer your question, Gene?
Sort of.
Yeah, sort of. Yeah, David.
So, in realclimate.org, like a day or two ago, they alluded to a paper where they, and the link was dead, but apparently we're not monitoring the Arctic as closely as we should be, and they attributed the lack of surface warming to missing some of the Arctic. And a lot of the warming is happening in the Arctic.
I have seen that paper, or I've seen the press release that came along with the paper today. And that is a possibility. I mean, the Arctic is only 3% of the surface area of the ocean, if that. And it would have to be a lot of warming in the Arctic in order to cause that to compensate for that downturn. But you are right. Most of these global temperatures do not include the Arctic, and so that would be a problem.
So why are we missing the Arctic? That seems like an important, at least from satellites, it's not that hard to, is it?
It is, because it's covered by ice. And you can kind of get the temperature measurements from leads between the ice, but when there's ice there, you can't really get temperature measurements. So we just need an ice-free Arctic, and then we can get temperature measurements all the time. Yeah, Gary.
So the other thing that's always bugged me about the sea surface temperature versus the heat content,
Yeah.
having a different rate. The interesting thing is over the same time, remember the proposal you sat in on the office with Mark and I,
Yeah.
Steve, is that also is the same time period where we've seen the atmosphere seems to be in a more energetic state
Mhm.
of perpetual La Nina,
Mm-hmm.
which should increase mixing rates.
Yeah.
So you could imagine if you spread the heat over a bigger depth, you can keep the sea surface temperatures
Yeah.
similar. But that's a puzzle, though. The SST versus the heat content
Well,
are not doing the same.
Yeah, yeah. But actually, Dean Remick, and we address this a little bit in the chapter, has a nice little study with the Argo that shows during La Nina there tends to be a transfer of heat to the deeper ocean, and during an El Nino it's reversed.
Well,
And
that's what
so-
I'm
yeah,
saying.
yeah, exactly.
We've been in a
Yeah,
long-term
yeah,
La Nina
yeah,
state,
yeah.
energetic
And
state.
that would be tending to mix the water deeper, that mix
That
the
would
heat
have
deeper.
the heat content,
Yeah,
with the
yeah,
sea surface
yeah,
temperature,
yeah.
not so much.
Yeah. Bob?
But there's also a lag time between what goes on at the surface and how long it takes to
Oh, yeah. Yeah.
transport the stuff
Yeah.
in.
And it may be that we see a slowdown in the heat content in the next 5 years or so. But we'll see.
Right.
Yeah, yeah.
So, but one, you can't just look at SST now and look at heat content. I hate to use heat content. 'Cause heat's not a state variable, but
Yeah.
internal energy content.
Yeah.
And then, say that they're not behaving the same
Yeah.
because they shouldn't.
They should. No, exactly. And that's honestly why I prefer looking at energy, ocean energy content than sea surface temperature or sea level, either one of those. All right.
How about the atmospheric temperature right along the sea level? Is that also the same constant, or has that not been measured?
I don't really know, because we look at the atmospheric temperature over land and it's kind of going up a
You had
little
the figure
bit.
at the very beginning, though,
Yeah.
of the global.
Yeah, but that's dominated by sea surface temperature. That's really dominated by sea surface temperature.
So it will
Yeah,
increase in these.
Yeah, yeah. So anyway, let's talk about attribution of climate change. Running out of time a little bit here. The way we attribute climate change, i.e. it's anthropogenic or it's not anthropogenic, is we have to use models, right? We run the models and we have to make sure that the models match observations, right? If we cannot match the observations, then the model is no good. And we run the model with only what are called natural